if she keeps it in the same order every time, then potentially Evan could figure this out and just like know what like encrypted output goes with what output. And so like that would be a problem. And we really don't want any information to go to Evan at all about what Ginny's input was. Now the next part is probably the most important part. It's where Evan actually evaluates what the output of the function is going to be. So in order to evaluate, Evan needs to get the specific random label that goes with her choice bit G. And so like because it's just a random label, it doesn't tell Evan any information about what her choice was. But once again, she can't just give him both of her random labels because then he can decrypt multiple garbled outputs, multiple encryptions. So like when we go back here, like he's always going to know whatever his like random label is that goes with his choice. But if he had both of Ginny's random labels, he could compute 2 hashes or 2 secret keys and then decrypt 2 of the garbled outputs. Okay. And the way that this is possible is for like Ginny to give Evan the random label is just out in the open. Because it's a random label, nobody else like is going to be able to use that information to like do any harm without the other random labels that are associated with Evan. However, there's another piece of information that Evan needs, and that is the specific random label that goes with his choice. And so, once again, it's the same sort of situation where we can't give both of the random labels to Evan, because then he would be able to decrypt more than one output and compute more information about the function. So this is where, finally, Oblivious Transfer comes in to play. So we have Evan's specific choice, throws it into the Oblivious Transfer function, and we have Ginny with her 2 random labels that go with whichever output that, or whichever input Evan has, and she throws those into the function, and then the function spits out the specific random label that Evan needs. It's very nice, and now nobody is getting any information that would allow them to like figure anything else about the problem. So now that Evan has these 2 random labels that go with each person's specific choice and no extra information, he can compute the secret key that goes with those labels, and using that secret key, he can decrypt one of the outputs. So either 0 or 1. And then usually there has to be, well, it's okay, we'll get into that later. Are there any questions about what, like the basic stuff about garbling is? Like just like the process. No?
So
Yes?
just to be specific, Garbled is like entire process that you just described was like sending and using Oblivious Transfer, or just like a specific part of this process?
Right. So we'll that's sort of something that we'll mention at the very end, but like I might as well mention it now. The way it works is you go gate by gate. So like each of these, whether it's an AND or an OR, like these are gates. And if you want to encrypt a larger circuit, you use the outputs of these as more labels. So like the output of this one is just like, it's got 2 possibilities, and you compute the random labels that are associated with that. And you just use those labels when you're trying to garble this one. So that you can start from the bottom, and when he gets the decryption of this gate, he'll get actually just a random label, which he can then use to decrypt decrypt this one, top gate. So a good question. Okay, getting a little bit more fun. This is a neat idea called something that is perfectly secure. So we mentioned like Visionnaire and Caesar ciphers. Both of those are pretty easily like broken nowadays. It might not be obvious right away, but there's something called like, oh, what? Actually, I don't remember what it's called. But you can use statistics to like decrypt something when you have the block size, a given length of the Visionnaire. The Visionnaire is the one where you encrypt a word using like 0, 1, 2, like multiple numbers. So if you know the size, and you can guess the size, or you can approximate the size using like some I mean, like you could guess like first, okay, it's going to be 0, then, well, you can't say 0, but 1, 2, 3, and 4, and so on. Like it's not going to be too large because it has to be a number, or like some sort of number that they can remember. And so you can use it to like, you basically use, there's a certain like distribution of letters in whatever particular language you're using to like encrypt or decrypt. So if you take each random like arrangement of the letters in that language, and you can see like, okay, there's so many of these J's, and there's so many of these X's, and there's so many of these Q's, you can actually rearrange them so that you're figuring out which letters are which. But that's not too important. Basically, the idea is that Visionnaire is easy to crack. Some other function, like encryptions, are also very easy to crack. But there's one thing that is actually provably impossible to crack. And this is called a one-time pad. So the way you do it is like, you've got some sort of key that is the same length as your message. So this is sort of like weird because it's actually very expensive to perform a key transfer. So if you wanted to like key transfer something that is the size of your message, you might as well just like, you know, get them your message in the first place. But the nifty thing about this is that no one can crack it. So the idea is that you've got your key. Just go with, I mean, say we're trying to like send the message apple cat, and our key is going to be cat apple. But in real life, you'd want to do something that is completely random. And so then, in order to encrypt, you're just going to add these two things together. You add them. I'm not sure what the addition is of this, but yeah. So if you want to know, like, okay, I'll try it. So a plus 3, that would be like d. B plus a. Wait, no, let's see, actually. A plus p is p. T. I'm not so sure. But yeah, so if you don't understand why it's perfectly secure, let's say the only message you get is just a random sequence of letters, A, G, A, C, K. That's your message. And you're trying to figure out, okay, what was the original text? The key is the exact length as the message. So no matter what you try, you're like, okay, let's guess that the key is actually, I don't know. I'm not sure. House P. So you try to subtract it, you get some sort of thing, but that doesn't tell you anything about what the original message was. It doesn't even tell you if you're close. You could guess any sort of arrangement for here, and it would actually get you like a specific output that essentially you're the only one deciding it, because you're the one deciding what the key was. So like, yeah, you could subtract something that would make this into a word, but you have no way of knowing that that word was the person that was the word that they originally chose. And this is seen to be actually something that's even easier to do with binary. So if you want to use a function called XOR, that's basically addition, but you don't even carry on any numbers. So you just have 0 plus 0 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1, and 1 plus 1 equals 0. You get your whole string of zeros and ones, and you get another one, that's your key. And I don't know if these are the same length, but they should be. And then your encryption, you just do this same sort of function over it, and the result is you get something that you cannot decrypt. But there's actually like a lot of really interesting crypto systems out there. There are some that are like completely random, so like you get a different output depending on like, I don't know, you encrypt it one time you get one output, you encrypt it another time you get a different output. But either way you can decrypt those outputs using the same key, and you get the same message as before. So if you guys want to like, I don't know, just discuss some of those, we can talk about them later. Do you guys understand why like this sort of using a key that is the same length as your message makes something that can be like provably perfectly secure?
Wait, actually,
What's that?
so like, why can't I just use statistics again?
Oh yeah, okay. So that's like a really cool thing. I'm gonna erase this board to talk more about that. He left. No worries. Yeah.
No, he actually just needed to go with your homework.
Okay. So you've got like a certain distribution of letters in the English alphabet, for example. And so on, you know, whatever the letters are. And you've got like, okay, so there's a certain amount of A's in a block of text, some fewer B's, lots of C's, and so like, you know, you get lots of E's and T's and all this stuff.
Hey Will, you're in the camera eating. Can you take the whole box of food to this spot or to Anisha?
I'm however many of these there are. So like the actual like distribution is different for different languages, and it's not like too important. The idea is that given a certain alphabet of swapped letters, you can rearrange it, because the idea is that if you're typing in a certain language, there's going to be a given like pattern where you can see the letters that are used the most, and then you can just realign them. So like if we have, you know, whatever our alphabet is now, it's like Z, G, H, K, I, P, you know? So we just randomly swapped everything around. But if you create these same like bars, depending on the frequency, like how many Z's there are, how many G's, you can rearrange them so that they line up with the original letters that they go with in the English alphabet.
Oh, but since we use a different kind of key for every letter, that the
Yeah, so
this is
so you're only going to have one example to try to like get this whole bar graph of frequencies. So you can't use it on a one-time pad. But if you were using like only a key of like 5 numbers across the whole text, then you can do this sort of thing where you split it up into, so you have an alphabet for all of the first of every 5 letters, and then an alphabet for the second of every 5 letters, because that, yeah?
Keep going on the question for after.
Okay, so yeah, because like, let's just write a sentence. Like the, I don't know where that marker went that worked. Okay. The dog There's a cat. Fox. The fox jumped over the lazy dog.
It's a sentence that contains every letter of the English alphabet.
Ah.
What's up?
This
You
is a
missed
sentence that
Rick
has.
Brown.
I'm sorry.
Human being.
Okay, so if you have like maybe a key of 4 numbers, 5, 8, 4, 3, and then you just repeat it 5, 8, 4, 3, 5, 8, 4, 3, and so on. Then you can create like one of these graphs for each of the letters, or like each of the numbers in the sequence of 4. So you've got like a T here and an O here. It doesn't matter because every time that it lands on a T on this specific like location in this index, you're going to get the same number or like the same letter in the encrypted text, because each time you're just adding 5 to T. And so then you can like get these frequencies, mix them up back to the way that makes sense with the English language, and figure out what the text says. But this has nothing to do with multi-party computation. I just think it's cool.
Will has a question.
What's up, Will?
So if you're using an encryption system that's like, where the key is not the same length as the text, let's say like, I don't know, length of the text -1 or something, like just shorter, is it then like able to be cracked somehow, or does it?
But that's not enough, right?
Yeah, it's. I mean, if it's less than the key -1, it's kind of basically it's like the same thing almost as a one-time pad. But the idea is that it's still hard to send a key of like length of the message -1.
Yeah.
And you know, it's not that much of a huge difference. But maybe if they figured out that you're doing this and you're just being lazy, they could eventually decrypt it, or at least do better. And also, if you're being this lazy, you're probably like making some other problems because.
Yeah, but like, is it provably? Is it like? It's only impossible. It's provable that it's only impossible to crack when it's the length of the message, not one less.
Right.
Wait, really?
Yeah, because okay, if you know, or it's not necessarily possible for you to crack the whole thing, but the idea is that if it's perfectly secure, then the people should know exactly what you're doing to encrypt it. And so if they know that you're using a key of like length of the message -1, then they can probably do some sort of guesswork because you're going to keep using this encryption scheme for multiple messages and so on and so on.
So over many years.
So like eventually they can figure out what the first and last letters are of your message. But you know, it's kind of, yeah, I'm not sure. Next thing. Oh wait, no, I forgot to
Wait,
mention.
I'm sorry.
Uh-huh.
Do you bring that with Will? I kind of don't get it. So basically, you're saying that if you have an n-1 keyword,
Yeah.
right, and if you would have like the same n-1 keyword but like a bunch of like n type of messages, you could crack it. But if you have like an n size like keyword and n size message but just a bunch of them, you still can crack it.
Yeah, you can't crack the whole thing because like for the message that is like kept inside, like you basically have the same thing where it's just like a random length.
No, but if you have like enough of it for statistics again, like say if my n is like small enough, and I can like predict a probability of like, you know, like a specific number, a specific like letter coming together, and then I figure out what are like, you know, my probabilities, and then I match them somehow. Like I think you can do something with that.
But what if for every, wait, is this assuming that you keep the same key for them each? message and each message is
by
in the same
definition,
length.
in a one-time pad,
Yeah.
you only use each key one time.
Okay, so then the
Okay.
key changes.
Yeah.
So the key. So the key changes.
Yeah, the key
Okay.
changes.
Okay. That would make sense. That would
But
make
in
sense.
order
But
for
it's-
something to be like perfectly secure, you can't get any information about the message at all. None. Not anything.
Okay.
Not even the slightest probability. So, you know, if you know like a certain thing about the encryption scheme that makes it
So
slightly different.
any information about about what's actually behind the encryption must be random. Like,
Yeah.
must be a guess.
Yeah. But nowadays people use different types of encryption schemes. They don't use this one because it's expensive, but there's another cool one called AES, or what is it, Advanced Encryption Standard, that uses like really cool abstract algebra and like matrices and all this stuff. So maybe if you guys wanted, I could talk about AES some other time.
What do you call them? Cryptologists?
Cryptographers?
Cryptographers? Oh, yeah, that would make sense.
What's up?
They, like, when they go about proving this,
Wait, is that sleeping?
It could be.
Oh.
they,
Cute.
like, how do they, yeah, in system of time.
So like they have these really neat definitions about like whether something is secure or computationally
Cut it.
secure,
Yeah.
or like if there's like a probabilistic algorithm that can do something, or a polynomial algorithm that can do something, deterministic and all this stuff. So it's like, yeah, like if you want to know, I've got a cool textbook, I can send it to you.
Send it in the group chat.
Sure. This is how to do the thing that we did with like paint cans earlier, but it uses math. So I don't know how much you guys like math, but here it is. So
Wait,
basically,
explain what mod is first.
yes, mod is division without like actually taking the the thing that you get from the division. You just take the remainder. So like if we have 10 mod 3, what is 10 divided by 3? It's like 3.333, yeah. But we don't care about the first 3, we just care about this thing. And what is this? This is actually 1 out of 3. And even more so, we don't care about this part, we just care about the 1. This thing is called like the remainder. So if we were to write 10 divided by 3 in the way that we actually want to write about it, which is like 10 is equal to 3 times a number, times q plus r. We're gonna write, okay, so from this thing, we have q is equal to 3, and r is equal to 1. And what the mod function does is it just gives you r.
If r is less than 3.
Yeah, r is less than 3. Yes. So and like this equation is like good when r is less than 3. You've got like the maximum q that you can have. And r is still positive. Do you know what a mod is? Do you want to know any more information about it?
So you just take the remainder and nothing
Yeah, you
else?
just take a remainder.
So you can like a pretty good way to do it, or not good, brute force way to do it. You just keep subtracting q from your number until you get to a number that's less than q. So subtract. But q over here is actually just a prime number, specifically like a big prime number. P is also a prime number. So yeah, we're gonna pick a random number that is less than q. This is Alice. This is Bob. Bob is also going to choose another random number. This is essentially them choosing their private colors of paint. They're not gonna like tell anyone what these numbers are. However, they are going to use them when they evaluate q to the x, like q to whatever the random number is that they chose, mod p. Now q, this is their public information. This is like the public color of paint that they had before. So they can both compute like this sort of exponentiation in their modulus. There's a way to do this very quickly. If you want me to like talk about it later, we can do that, but it's not too important. The idea is that you get q to the x, or q to the a and q to the b over here. Then they send the information over, and in order to get their secret thing, they just compute that once again to the power of their secret number and to the power of their secret number. So, yeah, I'll just write it out.
Do you think after that we have to have a break?
Do you guys want a break?
I just don't know when people want to have a break. We usually have it after like 1 hour or something.
Yeah, you guys can totally have a break, or leave, or do whatever you want.
How much more do you have?
Like 3 more slides?
Wait, what?
Then you can.
Oh,
Yeah,
sure.
just keep going.
Okay, yeah, that's fine. Okay, so like, we have got Alice over here with her secret A, and Bob over here with his secret B. They both decide on a public number q. Alice computes q to the A mod p. Bob computes q to the b mod p. This modulus ensures that whatever they're doing is not that hard to do. It just means that like if they're normally when you're trying to do a really big exponentiation, you have to compute all these multiplications. But if you're doing it over a modulus, there's a way that you can quickly speed it up. Then they send this information to each other, whoop, back and forth. Then, oh yeah, and this way that they can use to speed it up, it doesn't work in the reverse. So when you give this person q to the a, they can't like compute a logarithm and get a from this information. At least that's something that these cryptographers have said is hard to do. And we're just gonna trust them.
What?
Will doesn't trust you, Cullen.
If you don't trust the cryptographers, that's actually probably a good thing.
Yeah.
There have been like some situations, you know, the NSA, they make the codes, right?
Yeah, they keep getting hacked, don't
They keep getting hacked, but they also hack you. Because when they make these codes, sometimes they publish them with like, oh, you should use these numbers. These are good numbers that you should use to encrypt. And then the actual like situation is that if you use those numbers, then they have some sort of trapdoor function. They can go back in and decrypt anything
So
you
use
use.
those numbers.
Yes. Just generate your own numbers, but do it in a smart way because some numbers are bad, as evidenced by the NSA.
I think prime numbers are good, right?
Prime numbers are
My
good.
numbers are good.
Okay. Yeah, so they say it's hard, we're gonna trust them. Then you go back, you take this q to the b that was just given to you by Bob, and you take it to the a, mod p. And Bob does the same thing with q to the a to the b, mod p.